few people might show up a little bit later, so we'll try to save the good stuff for later. So we talked last time a little bit about dark matter, and it was so exciting that you guys wanted to do it again. So we're gonna go into a little bit more depth. All right, it's gonna be great. Specials on dark beer. So $5 for the 2 dark beers that are on tap right now. Yeah. Awesome. Thank you, Brandon, for letting us do this. It's super fun, and I've been kind of on this all week. And I actually talked to my buddy out in Hawaii who works at the Keck Telescope, and we got nerding out for probably about 45 minutes today on dark matter and some ideas behind that. I'm going to try to make it nice and easy for everybody to understand as well as I can. I got a whiteboard this time, so instead of using my hands, because I don't know what to do with my hands, I'm going to try to draw pictures and make it a lot easier. All right, and if you guys are interested, we can even do like crash course particle physics or something like that, because matter, like dark matter is matter, you know. Dark is really kind of an inappropriate word to use for it. I'm going to reference a lot. I actually took this, I grabbed this book from my library. This is my celebrity crush. If you ask me who my celebrity crush is, it is this person right here. Hey guys, this is Lisa Randall. She is the professor of particle physics and cosmology at Harvard. And I have pretty much everything she wrote, and I've seen every available lecture I can get from her. And she's absolutely brilliant. And she wrote this fantastic book, Dark Matter and the Dinosaurs. We're going to go into what she kind of figured out, the correlation between dark matter and dinosaurs. This is going to be really cool. And you can extrapolate from that later. I'm not going to spoil it. All right, so first of all, and I'm going to reference her a lot. Dark matter is really it's really disingenuous to what it is. It's really a lot more appropriate to refer to it as transparent matter. We only call it dark because we don't understand what it is. Okay? And it makes it sound kind of scary. You know, things that we don't understand, things that we don't know what it is, it makes it really scary. And what's crazy is when we figured out that it actually does exist, we found out that there's quite a lot of it. So I'm going to do like kind of a hybrid between drawing pictures and doing slides. I'm riffing here. I don't have that many notes because I don't feel like I need that many. I love this subject. It's fun. So we talked a little bit last time. We're made out of atoms, you know. Atoms are made out of protons and electrons, and neutrons. Those are made out of constituent parts, which are called quarks. There's neutrinos. There's bigger versions of quarks. There's bigger versions of electrons. There's bigger versions of neutrinos. There's photons. There's the Higgs boson. There's all these particles out there, but all those make up stuff. You know, stuff. Really, really, really fast. And I mean really fast. So fast that when he ran his calculations, the galaxies should have actually not only flown apart from the cluster itself, but they should have torn themselves apart completely. Like the stars could not have stayed together inside of their galaxies. It's a crazy idea. So he came up with this idea that there was like this missing matter, like there was more matter in the galaxies than we measured just by traditional means. And when he calculated it, he measured that there was 400 times more matter in these galaxies than what we would normally measure. 400 times, that's huge. So he came up with this idea, and he called it dark matter in 1933. And nobody listened to him. Everybody said he was crazy. And as much of a veteran as he was at measuring things, I mean, he did more surveys than anybody. Nobody trusted him. They said, okay, it's just Fritz Wiki with some crazy idea. You know, nobody listened to him, and they threw his idea completely into the trash bin for a long time. And then this other lady comes around, Vera Rubin. She's done a lot of fantastic stuff. She was an amazing astronomer, amazing woman too. So she was actually looking at another cluster of galaxies called the Bullet Cluster of galaxies. And she wasn't looking at the galaxies actually moving apart from one another. She was actually looking at how fast they were rotating. This is really interesting. I'm going to start drawing pictures. I think it's going to be fun. All right. So some of you were here last time. We went over the basic, you know, laws of angular momentum. I promise not to do any like equations or math or scary stuff tonight, but I got a whiteboard. We're gonna use it. Can I get like a wet paper towel and a dry paper towel? Because this like eraser doesn't work really well. I didn't think about it. All right. So let's say we have a galaxy, okay? Now, in the galaxy, you have a core of a galaxy, and then you have these spiral arms, okay? I'm not very good at drawing anything. I can draw like a cow, and I can kind of write my name. That's about all I can do. A cow jumping over the moon. It's appropriate. Okay. Now, the people that were here at my last talk, I said that the harder you pull or push on something, the faster it moves. It makes sense. You know, if you pull hard on something, it's going to move at you faster. If you pull gently on something, it's going to move a lot slower. Okay. Now, we know now that in the middle of every single galaxy, there's a supermassive black hole. Supermassive black hole. And all of the stars, including our sun, orbit around this supermassive black hole. It obeys, you know, the same laws that our solar system obeys, in that, you know, the closer you are to the sun, the faster you move around that sun, our sun. Mercury moves really, really fast. Venus moves a little bit slower. You know, Earth moves a little bit slower. Mars a little bit slower. When you get out to Pluto, it's moving kind of slow. Okay, because it's not being pulled by our sun that hard. It's being pulled a lot softer than something that's closer to the sun. Now, galaxies kind of operate the same way. There's this huge mass of gravity. There's this gravity potential in the middle of the galaxy, and it's pulling on the hundreds of billions of stars that are in this big, you know, loop around it. Now, what you would say is that the stars on the inside would be moving really, really fast, and then the stars on the outside, because they're not in this gravity well that's making them move really, really fast, they're going to move a lot slower. Okay, a lot slower compared to the stars on the inside. So that's what everybody thought. Everybody thought this. Now, Vera Rubin, with a team, but she was kind of the baddest of the team. So that team went out and measured the velocity of the stars on the outside of galaxies in this bullet cluster, and she found that the stars on the outside were moving at the same speed as the stars on the inside, which didn't make any sense at all. This thing has a mind of its own. Oh shit. Okay, Roomba, chill out. Okay, we're good. Ooh, dark energy. Okay, freaked me out a little bit. Okay, so when they figured that out, it's really interesting. I thought of a really good example to explain how this works too. What she figured out was she actually went back to Fritz Zwicky's papers and realized this guy I think he was right. There's this missing matter. It was a missing matter problem is what they called it back then. And now we call it dark matter. It's actually there. And this is, if you ask anybody who's kind of interested in this kind of thing on the street, how do we know that dark matter exists? It's because of the orbital velocities of stars in the outside of galaxies. It's like if you meet a nerd, that's what they're going to tell you. There's more things that prove it that I'm going to go into in a minute, but this is the first bit of evidence that we did. And this was in the 70s, okay? So I thought of this. I was watching this lecture from the Institute of Advanced Research, and this guy had a really cool model. And think of it this way, okay? So dark matter exists within this galaxy. There's a lot of it, okay? And it's kind of homogeneous. It's about the same all the way across. So there's this extra bit of gravity, extra bit of mass or potential gravity that exists all along this plane of this galaxy, if we look at it from, say, the side. Now, imagine that you have something like in the middle of a table or something, or on a bed. And imagine you drive a spike into something, and you take a string, and you attach it to, say, like a tennis ball. And then you twist the thing in the middle, and then you see that this long string that's attached to this tennis ball starts twisting with it. Imagine how long it takes for something to influence this tennis ball from, say, here to over here. Let me draw. I can draw pictures. Why am I not doing this? Where did I just put that pin? This is great. Okay. Good. Okay. So if you have something here, you have a long string to something attached over here, and you start spinning this way. Okay. This will spin quite a ways before this actually starts feeling anything. Okay. But imagine if you had a string here and it was attached to something here. Okay, and then this was attached to another thing here, and this was attached to another thing here, and this here, and this here. because you have more things that are feeling the gravity in between, it's actually going to have a much stronger impact on what's happening on the outside. Everything's going to move in a much stronger way, much straighter way. And that's kind of what's happening with dark matter, where because dark matter exists in everything, as the galaxy actually starts spinning, everything is, honestly, the stars out here, they don't even feel the black hole in the middle, okay? So as this is spinning, they're actually feeling the gravity of not only the stars around them, but they're feeling the gravity of this huge amount of dark matter that overwhelms the gravity of each star. All right, do I have you so far? Does this make sense? Any questions so far? Okay, good. So it completely overwhelms that. And it has to be. It really has to be. Because if this matter was not there, if this dark matter was there, you can actually run the calculations. You can see how fast the galaxies are spinning, and you would actually, the only thing that comes out of that equation is all these stars on the outside of the galaxy would fly away. The galaxy would never hold itself together. The only way a galaxy can hold itself together is if this dark matter actually exists here to hold it all together. So the first profound thank you to dark matter is galaxies couldn't exist the way they do unless dark matter was there to hold it together. Okay? It's pretty cool, huh? Super, super cool. All right, let me make sure I didn't miss anything. Cool. So it's funny because Fritz Zwicky, he measured, and I want to make sure that everybody knows this because he was wrong about something. He measured 400 times more matter than there should be, which is not right because, hey Mason, what's up? So let's go back to this. I don't, okay. So ordinary matter is 4%, 21% dark matter. 21% is not 400 times more than 4. I mean, this is not hard math for anybody. On average, Vera Rubin actually concluded, I think, 6 times more matter is what she got, which is pretty darn close. Pretty darn close. All right. So that being said, this is how we discovered for the first time that it actually existed. This is absolutely profound. And ever since then, we've wanted to know what it is. But we ran into a lot of problems. The reason we call it dark matter is because we don't know what it is and we haven't been able to detect it yet. And the question is, why not? We've built large particle accelerators, and I would be happy to go into, I mean, people who know me close enough know that I would love to go into particle physics at any time, and I would draw out the standard model for you and explain it. But we've been building these large particle accelerators like CERN, the Large Hadron Collider in Geneva. Okay, and we're colliding protons together at nearly the speed of light. They smash into each other and then they break apart, and then we measure what it breaks apart into. Okay, and we've recently actually discovered something that was, you know, it's probably going to exist, and that was the Higgs boson. We actually figured out that the Higgs boson really does exist, and that's fantastic. There's actually a model, I'm going to get into the models later, but there is a model of dark matter that says that it would be a particle that would be a little bit more massive than the Higgs boson, and it took this much to build a particle accelerator to get up to the energy potential to create a Higgs boson.
What is a Higgs boson?
What is a Higgs boson? Okay. Are we cool with diverting for a second?
The God particle.
Yeah, okay. So, no. If you ask anybody at CERN, or if you tell them that it's the God particle, you know, yeah, they'll probably slap you. They hate it, but they love the publicity, I mean, at the same time, you know. So, the Higgs boson, or the Higgs particle, the Higgs mechanism, it was first kind of put out there by this physicist named Peter Higgs. That's why we call it the Higgs boson, this guy Peter Higgs. He didn't, I mean, everybody refers to him, but the people that discovered it on the team, I think it's this happened July 4th, 2016 is when we discovered the Higgs boson. So I think it's the largest recipient of a Nobel Prize, not as far as money, but the amount of people. I think there are, 6,000 people that were noted on the discovery of the Higgs boson. I think it might have been 3, but thousands of people that are recognized for helping on this, because it took so much in the entire world, dedicating all these funds to discovering something. And why was it so important? What is it? So you weigh something. Some of us more than others, like me. Okay, so we all weigh something. But where does that come from? Like, why does anything weigh anything?
Gravity.
There's a gravity. Okay, so what about a photon? What does a photon weigh?
Very little.
Nothing. A photon weighs 0. It has no mass. Okay? So why do certain things have a certain amount of mass? What grants mass to particles? Okay? So there was this idea a long time ago about the ether. There was like this ether out there. It's kind of like if we lived in a big bowl of soup and we're all peas and carrots. There's still like the liquid of the soup that we're all passing through, right? Okay.
Space was the ether.
Space was the ether, but I mean, what is empty? If you take everything, all the energy, everything out of empty space, it's still nothing. You know, if you take everything out of empty space, it's still nothing, and that's still true. So if things pass through space and there's no resistance, then it essentially moves at the speed of light, the fastest something can pass through space. But when things are slowed down, what makes them slow down? This gets really complicated, but I'm going to try to make it understandable. So I've always thought of it as imagine being in like a pool or in the ocean or something. Okay. Now, if you take your fist, I don't know if you've ever done this. You do it when you're a kid, but you put your hand in the water when you're in the water, and you move around slowly. It doesn't take that much resistance. Like there's not a lot of resistance on your hand stopping you. But say if you push it really fast, you put a lot of energy into moving fast. The water itself is actually what's keeping you from moving slower, from moving faster. It requires more energy to push your hand through that water, okay? As opposed to like just say air, like what we're doing right now. It's like, it's nothing for me to do this. Okay, so, but if I do that in the water, it takes a lot more energy to do that. The water restricts me from doing that, okay? And if I wanted to move at the same speed in water that I did in air, it would require more energy, more calories, more of everything to make that happen. The Higgs mechanism is essentially, it's basically that field that's around particles. When particles pass through this field, it imparts a resistance on that, and that resistance correlates with the energy that it requires to move through that, in the same way that like a hand moves through water. It takes more energy to move at a certain rate. This is why certain things require more energy to move faster. Okay? I don't know if you've heard this idea that if you have any bit of mass, you can't move the speed of light. And then you ask, why can't you? It's because you would require all of the energy that the entire universe has to put into you to move at the speed of light. Therefore, you would become the universe. I mean, it sounds bogus, but it's actually true. You know, we're moving through, if you have mass, it requires all the energy of the universe to get you moving up to the speed of light. Light has no mass. Therefore, it can travel at the speed of light, the fastest thing anything can propagate through space. Have I lost you yet?
No.
Thank you. Yes. Oh.
We're with you, brother.
Yes. All right. Cool. And that is the Higgs mechanism in a nutshell.
But I'm still 2 turns from Thursday.
Okay. Okay. Oh, I'm so glad you guys got that. Oh, I've worked so hard to try to explain that as best as I could.
Thank you.
Okay. Awesome. Oh, okay. Where were we with dark matter? Okay. So we know dark matter exists. Let's talk about what dark matter does. Like, what are its properties? Okay. Now, we are ordinary matter. We talked about this last time. Ordinary matter, think about atoms. Atoms have a nucleus in the middle. I'm going to draw pictures because I can. This is great. Okay. Yay. I'm so excited. I'm just explaining it. Okay. Okay, we have a nucleus of an atom. Okay? I should draw bigger because I can. Okay. We good? Oh, okay. So we have a nucleus of an atom, okay? I'm going to use a hydrogen atom because it's the easiest thing because there's only one proton. Okay, we're not going to get into neutrons and stuff. Now, we have a proton in the middle which has a positive charge. Okay, a proton has a positive charge. On the outside of that proton, you have an electron that tends to do this orbit thing. And we're not going to get confusing. Orbit is really not the best way to describe actually what's happening, but it's easy for this description. Okay, so on the outside of the proton, there is an electron that's orbiting at a very specific orbit. It can only occupy this one orbit. Only this. It can only be here. It can also be here. It can also be here. Okay, these are certain energy levels that an electron can be in, but it can't be here or here or here. It has to be one or the other. Okay, it's quantized. It has to be a very specific thing. This is a very profound thing to understand. Now, these electrons on the outside. Let's say we have another atom right next to it. Okay, another atom here, and then we have another electron that's negative. That is positive. So. On the outside of every atom, everything is negatively charged. And what do like particles do? What do like charges do when they come into contact with one another?
Split.
They repel each other, okay? Opposite charges attract, like charges repel, okay? Every atom has electrons on the outside, and everything's made out of atoms that we're made out of, everything that we know, everything's made out of atoms. Keep dancing back there, I love it. It's getting me pumped. We need a little bit of background music. You should play that German band, that's super awesome. Is it not working? Just quietly.
No, I want to hear you.
I know, but super quiet. It helps me.
Okay.
Is that okay? There's no words in this music.
Just play it like ocean.
Yeah, it's good. Okay, we're getting good here. And I gave the example here. Now, what keeps me from going completely through this Pepsi cooler? What's up, buddy? What keeps me from going completely through this? I am made out of atoms with electrons on the outside. This thing's made out of atoms with electrons on the outside. And I can't go through because it's cool. I'm actually not touching this. Like, nothing's touching everything else. There's mostly empty space. Everything in here is essentially empty space. Okay? This is repelling me because of the electrons on the outside. They're not letting each other pass through it. Okay? Got you so far? Now I'm going to explain light really fast because this is really important to understanding dark matter. So, a photon, I call it the hot pocket of energy. Okay, so photon, this is photon. That's a symbol for a photon. Looks kind of like a Y. Okay, so photon here. When a photon travels, when it hits something, like an atom, okay? It actually hits the cloud of electrons here. So let's do it on this one because it's nice and clean. So a photon comes in, and it hits this. The electron on the outside of this atom actually absorbs the photon of light, this particle of light. And with that energy, it actually jumps to a higher orbit, okay? It jumps to a higher orbit. And then everything wants to be in its lowest energy state. This is like just a really standard, concept in the universe. Is everything wants to be in the lowest energy state. Everything's lazy. Nothing wants to work hard at anything. The universe is obviously a teenager in its evolution. So, but it wants to be back down this low. When it does, it will jump back down and emit a photon of the same energy. Okay, energy is always conserved. Okay, it always does this. This is how ordinary matter works. Dark matter is different. This is how everything works, by the way. Everything. Certain colors absorb a bunch of energy, a bunch of light. Certain molecules or arrangements of atoms, they have all the electrons over here, and then there's another cloud over here with more electrons, and another cloud with more electrons. When they absorb light, when they emit the light essentially, the photons that leave the atom there's a shadow that's essentially cast by this cloud of electrons, and that shadow cuts colors out of the spectrum, and that's where color comes from. Like, why isn't everything just white if this one mechanism works? It's because there's different atoms out there, and when light comes in, and there's this complicated mess of electrons, but it still absorbs the light, when that light gets re-emitted, this is not totally true, but it's an easy way that gets you close to understanding it. The light that passes back out, it essentially loses a bunch of colors because there are shadows cast. Certain parts of the spectrum, the entire rainbow spectrum, are basically cut out of it. They're shadows of the electrons. And that's where these colors come from, these different colors. Again, not 100%, but it's close enough to get you to understand the concept. Okay, dark matter is completely different. So light interacts with ordinary matter this way. But if you remember in the last thing we did, dark matter does not interact with ordinary matter by way of light. let's say you have an atom. Let's say you have something. Dark matter, or light, anything. Light goes completely through it, and dark matter doesn't even know it's there. Which is very strange. Very, very strange. So, I shouldn't have erased it so fast, but you'll know what I'm talking about. Now let's take the same two hydrogen atoms, for instance, okay? They have these electrons on the outside, they have a negative charge. Let's say two of them are kind of cruising through space. They're small, but they still observe gravity. Everything kind of observes gravity. Even photons, which have no mass, observe gravity. They can bend. We're going to talk about that in a second. So these two hydrogen atoms, very simple. Everything does this. Carbon does this. Oxygen does this. Everything. They're going to, because of gravity, they're going to start falling towards each other. But when they, let's say that there's an opportunity where they can actually touch each other. What's going to happen? They're going to bounce off of each other. Those negative electrons are actually going to make them bounce off each other. They're going to interact in a way where they're going to lose energy, they're going to smack into each other, and then recoil from that. They're going to bounce around, bounce around, and bounce around, just like taking two tennis balls and smacking them into each other. Okay? That's how everything works. We already know that. You can do that with anything. Bounce a basketball on the floor. Dark matter doesn't do that. Dark matter, if it comes into proximity of ordinary matter, it comes closer, and it passes completely through it. Zero interaction. Dark matter does it with itself. Let's say, hypothetically, two dark matter particles. They come close, they're in a direct collision course with one another, they pass completely through each other like they're not even there. But they still have mass. They still observe gravity. They're still moving around. They're still going through this big pool of gravity wells in space. They still work the way that ordinary matter works. It's matter. It's dark matter. It's matter. It's not like a photon where it travels at the speed of light and it does this thing, has no mass. It actually has mass. It makes up most of the mass of the universe. But because it doesn't interact with ordinary matter, it doesn't make ordinary matter bounce off of it. It doesn't scatter light. It doesn't interact with light at all. But it's still there. Now, and we talked about this last time, and this is a really important thing to why the universe exists the way it does and why we're actually here in the first place. Now you think about this, when ordinary matter comes into proximity of each other, so let's say they're on direct collision courses, which is rarely the case, they're going to hit each other, they're going to bounce around, and they're going to clump together, okay, over a certain amount of time. Since dark matter doesn't do that, since it can pass directly through itself, it takes less time for it to collapse into something. Do you remember that? Yeah. It's a very important idea to bear in mind. Okay? Now, what are the implications of that? Okay? Remember when I was saying earlier that when we looked at the rotation speed of stars on the outside of galaxies, if there were no dark matter, those stars would fling out. They would fly away, okay? But because dark matter's there, they can hold themselves together. Okay, who here has heard did anybody take physics? Did anybody, like even basic physics? Most people? Okay, cool. You're familiar with this law of angular momentum? Okay, yeah, it's like high school physics, basically. And if you didn't take it, that's fine too. It's actually pretty easy to understand. Most things don't do that hypothetical thing I was talking about where they actually come into direct collision with each other. Everything pretty much does a near miss at some point. Very rare that two things collide direct head on. And when you have this near miss, let's say something is over here, and there's something over here. This is going this way, this is going this way. Now, because they're always bound together by gravity, they're going to be attracting each other. But as they come in, they're going to bend towards each other, but they're not going to hit each other. They'll get close. And let's say that at this point, this is their center of gravity. Okay? This is their center of gravity. Not where they are. This is where they are. Okay? This is where they are. But this is the center of gravity that they share. This is where the gravity is the strongest in the middle. What they're going to do is they're going to orbit that center of gravity, and they're going to whip around each other just like this. Okay? And they're going to lose energy in the process, lose kinetic energy in the process, the energy of their movement. Now, but still, since they're still bound to each other in this way, they're going to keep doing this. okay? And they're gonna wind down just like this. Same thing here. It's gonna constantly wind down, and they're gonna get closer and closer and closer and closer over time, okay? But there's actually gonna also be a point where they do bounce into each other, and they're just gonna do this for a while, okay? Now let's say that one in however many chances there are, that these two things here are in a direct collision course with each other, okay? They will actually, you ever use like a, what are those things called? A pendulum. A pendulum, how, you know, this ball comes down, hits, and that goes this way, this goes this way.
That's a Newton's cradle.
Newton's cradle, there you go. Pendulum, what am I thinking? Ugh, this beer is not strong enough. Okay. So you're actually, it's gonna take more time for ordinary matter to essentially collapse into something. Now, since we got that out of the way, what actually happens, and because they're still using gravity to do what they do, and dark matter can collapse sooner, because of this law of like angular momentum, things are spinning, and everything else is kind of touching everything else, and that's touching something else. Everything kind of follows the same pattern as they do this spiral. What you end up having is this big flat plane where things are spiraling this way. Okay? Kind of like pizza dough. If you spin it, it's gonna flatten out. Okay? This is the very beginning of a galaxy. Okay? Now, because there's a lot more dark matter, and because it still does all the things that we're talking about is doing, it's gonna flatten out and create what's called an accretion disk. And ordinary matter like stars and gas and dust and rocks and planets that form later, they're going to follow the same pattern that the dark matter has already set forth. It's already set the plane of where the galaxy wants to be. Okay? And when the ordinary matter kind of comes together in this accretion disk here, it makes a galaxy. This is where galaxies come from. This is a very chicken or the egg thing. This is not 100% proven, but it kind of makes the most. If you ask like any astronomer, what came first, the galaxy or the collapse of the dark? Everybody says it's the collapse of the dark matter. You know, the dark matter. Everybody, basically everybody. There's always that one guy, the contrarian. That one guy, yeah. It's, you know, he doesn't have tenure. He's a flat earther, right? He's a flat earther astronomer. Oh boy, any flat earthers here? Oh, thank goodness. This has been a lot more fun, though. All right. Disk of dark matter. We measure it. It's awesome. It's actually kind of thin, okay? Let's say that this flat plane, I'm going to start talking about really, really cool things about dark matter. So imagine that we're looking at the Milky Way. When you look up in the sky and you see that big stretch across the sky, that is the middle of our galaxy. Now, right here is, let's say this is the bulge, okay, of our Milky Way. This is where all the clusters of stars are. It's on the very inside. Now, all of the stars in the Milky Way orbit around the galaxy, okay? We're gonna do another galaxy here. This is a top-down view, okay? We're looking at the side view here, top view here, okay? Stars make up everything in here, and there's a dark matter accretion disk that makes up the entire galaxy here, flat this way, okay? And there's stars up here. There's stars kind of all the way around, but the highest concentrations of stars is all along this accretion disk, which makes sense because there's more gravity there to keep them there. Okay, there's ones that are loosely bound up here. You know, they'll fall in eventually, maybe, but most of them make up this middle section here. Okay. Now, since stars are moving, we're orbiting around our galaxy. It takes 220 million years for our star to go around the Milky Way galaxy. But here's a really cool thing. We're not just going around in a perfect circle or an elliptical orbit or anything. Every single one of these stars, because the dark matter is there, and this is another reason we know that dark matter exists, is that every star goes like this. You got that? It goes up and down. It's falling into this accretion disk of dark matter. It's doing that same law of angular momentum where it loses energy because there's less gravity up here than there is in the middle. It falls back down, and it constantly does this. It oscillates as it goes around. It falls in and out of this accretion disk of dark matter. Yeah.
So are you saying that the dark matter is causing gravity?
The dark matter, because it's matter, it creates a force of gravity. Like we're drawn to it. Yeah, and it's denser here in this accretion disk. It's because there's a lot of dark matter and it wants.
Contributing to the density of gravity?
Yeah. So let's say something is 10 pounds. If something is 20 pounds, it's heavier.
And create causing gravity. So is okay.
Yeah. Okay. So let's imagine that if you have like a 5-pound weight on a bed, on a mattress. Okay. If you put a 10-pound weight, imagine it's spherical. It's going to make a bigger dent. Okay. It's that's kind of how like a gravity well works, or a field of gravity works. Is the more mass something has, the more that I got one for you. I'm gonna make this really cool. So, who here has taken a ball and rolled it down a hill? Okay, everybody has? If you haven't, don't worry. This is true physics, so it's gonna be intuitive. Okay? So, if you roll a ball down a hill that is this steep versus this steep, which ball is going to roll faster? Yeah, the one that's steeper. Okay? Now, when you have more mass, you ever heard the phrase the fabric of space-time?
Yes, sir.
Imagine space itself as the fabric. If you have more mass and more gravity, you're essentially bending the fabric of space more because there's more gravity there. When you bend it more, things can move faster through it. Okay? So when you have that accretion disk of dark matter, things can move faster through it. It's bending space. And it's a little hard to imagine because we think in a certain way, but imagine that it's bending space but in every possible direction, in three dimensions. So instead of a two-dimensional plane like a fabric stretched out or a bed sheet or something, imagine that you do that in 3 dimensions. Instead of 2 here where it bends it here, imagine that something here is bending it this way. And the closer you get to something that is very massive, the stronger that feeling of movement is going to be. Okay? So the closer you get to the sun, the stronger the gravity is going to be, the stronger that influence is going to be. Okay? All right. Now, we got all that.
Cool.
Now, huh?
Cool.
Good, good. Okay, so what are the implications of that? What is the frequency of that, okay? Let's do the same thing again. Okay, accretion disk, middle of the galaxy, bulge here. Accretion disk, we're all moving up and down, 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 okay? We move faster when we get through here, slow down, faster and slow down, okay? Now, what is the period of this to here? What is the frequency of that? Okay, that's a good question. It takes us 220 million years to go around the galaxy as a whole. How long does it take to get from, one oscillation here to here, where we're on the bottom of the plane of the Milky Way to the top? The answer is about 30 million years. So that's actually a lot.
Measure that? Measure that?
We can absolutely measure that. We have a lot of, don't go on me. We have a lot of stars to measure. Okay, we can measure a lot of stars in our Milky Way. Now, here's what's really cool. Is dark matter and the dinosaurs. This is what Lisa Randall kind of figured out a little bit. She's not the only one that figured this out, but it's really something to think about. And this is, okay, I'm just going to explain it. So, how long ago did the dinosaurs die out? Does anybody remember?
65 million years.
Yeah, 65. People say 66. Close enough.
What about
Yeah,
your grandpa, Mason?
How did they die?
A gas cloud that was ejected into the dust cloud. That
Okay, he's wrong. Anybody else have the answer?
Asteroid hit the atmosphere.
Close. What's not an asteroid, but kind of similar?
Meteor. And it put dust in the air and blocked out the sun.
No, we're getting closer.
Black bastard.
What's kind of like an asteroid, but it's made out of different stuff?
Comet.
Yeah, there we go. It was a comet. Where'd that comet come from?
Interstellar space.
Yeah, okay. They came from space, yeah, just like everything.
Like the Martians.
Okay. Who,
We're getting too big for their britches. So.
yeah, totally. Okay, so who remembers what the Oort cloud is? Who is here? You've been here for all of them, okay? The Oort cloud is something that's on the very edge of our solar system. I might even have a picture of the Oort cloud somewhere. I'm not going to look for it. Okay, so in our solar system we have the sun in the middle, we have all the planets, all the way out to Pluto, which is in the Kuiper Belt, which is made up of 100,000 other little icy things. On the very outside of that, about maybe 2 light years away even, it can be out to that far, there's this big sphere, this cloud of ice, that the sun doesn't have enough gravity to pull it towards it, but there's nothing else on the outside to pull it away. So it just sits there in this equilibrium. It just sits there. There's not enough gravity to move it.
So it's the Lagrange point of the solar system?
Yeah, it's the Lagrange point of the solar system, essentially.
The Lagrange sphere.
Yeah, sure. I love it. Okay. So what happens when it's kind of sitting around our sun's moving around the Milky Way. What happens when suddenly there's more gravity to influence those things? They move. And where are they going to move?
Wherever the source of gravity.
Yeah. Well, I mean, there are 1,000 factors that can influence them at any one point. Some of them are going to be flung out into interstellar space. Others are going to be flung towards the sun. And as soon as the sun gets a hold of it by its gravity, it's on a free fall towards our sun. And imagine there's this giant hunk of ice from the Oort cloud that, because we've passed through this plane of dark matter, it's given us more gravity to deal with. It's now on a collision course with not only the sun, but with Earth. Earth just happens to be in the way at the time. And this big comet, because it's ice, hits Earth and kills everything. Okay, the dinosaurs, basically. Now, this is really cool. So, a team of scientists went out and started dating impacts from comets and meteors on Earth, major impacts. And they fall on 30 million year cycles. Okay? It's not 100% proven, okay? Just like anything in science, somebody's coming around to disprove it. But it seems like there's a real pattern here, that there's like a 30 to 33 million year frequency to massive impacts. What else happens every 30 to 33 million years? We go up and down and pass through this accretion disk of dark matter in the Milky Way. The fact that we pass through this is what gives those comets, asteroids, everything the potential to impact Earth. Okay? So we're here because the dinosaurs aren't. It's actually appropriate to say that the reason the dinosaurs aren't here is because they didn't have a space program. They had no way to protect themselves. We can nuke it. We have Bruce Willis. He's still around. It's fine. So, terrible. Okay. So, anyway, so where was I? So in a way, dark matter is really responsible for our existing here. The fact that we were able to evolve, that the dinosaurs were killed off and we were given an opportunity to make it to where we are. We owe our very existence to dark matter. The fact that dark matter collapses and creates galaxies, that allows planets to form around stars and have the structure it does. Everything that we are, we can kind of owe to the existence of dark matter. It's kind of beautiful in a way. There's no reason to fear it. No reason to fear it, even though it's dark. And again, if anybody talks to you about dark matter, you should say, "Oh, I think it's more like transparent matter. It doesn't really interact with other things." Okay.
Just like it interacts with gravity.
It interacts with gravity, but it doesn't interact with light or anything. So, but we still don't know what it is. Okay, we have this huge standard model of physics, but we don't know what it is. But there are some ideas being put out there. I'm not really going to go into the craziness of it because it gets. If it weren't complicated, we would have figured it out by now. And I tell you what, once you get into it, it gets really complicated, really, really, really fast. I'll tell you what. But I'll just write a couple of them down. Just because they have cool names. The one that everybody thinks it's going to be is called the WIMP, okay? Which stands for Weakly Interacting Massive Particle, okay? It's going to be a little bit bigger than the Higgs boson. There are hundreds of theories behind this. There's actually things called like WIMPzillas, which are like 100 times more massive than the Higgs boson. Good luck detecting that. There are ideas that did you have a question?
Yeah.
Yeah.
If dark matter doesn't
That's it.
interact with anything else, how can it interact with the rest?
Oh, that's a good question. Okay, so I want to be clear about that. So dark matter doesn't interact with ordinary matter in any way that we're familiar with, because everything interacts with light in some kind of way. Okay? And I explained this last time where everything here interacts with light, and you can tell because we can see each other. You know, light is interacting with us. You know, light just is not influenced at all by dark matter is not influenced by anything else. Everything else that comes into contact with dark matter passes right through it, including itself. Okay? And I actually almost passed over an entire section here. Oh my goodness. Another reason why we know it exists, and what it actually does to light. Because it does have gravity, because it has mass. In Einstein's equations, he actually predicted this thing where we would see light coming to us from the edge of the universe that's been bent because there's so much gravity. Okay? Now galaxies have a shit ton of dark matter in it. Okay, some have a ton. Actually, I just found out today, I was talking to my friend in Hawaii who works at the Keck telescope, and his girlfriend has degrees in physics and astronomy, and she's involved with writing papers for them, and I've actually helped her with a couple of papers. That's Fritz Wiki. Now, I wanted to explain this because this is really cool. I want you to be able to explain this to your friends if anybody asks you when you look at these pictures. So Einstein predicted that there could be so much gravity in one place, that light that moves around it can actually be bent because there's so much gravity. Okay? There can be so much gravity, like in the case of like a black hole, where light actually can't even escape because there's so much gravity in one place. Now he predicted this, but nobody ever seen it back then, and we saw it later. And he actually coined the term gravitational lensing. Okay, I'm going to show you a couple pictures of what gravitational lensing looks like. The one on the bottom right is a little happier than the one on the top left, but it's kind of crazy. It looks like a lens. So what's happening here? So you see the bright, like the top left one, you see the bright dot in the middle?
Yeah.
It's kind of hazy. That's actually a galaxy. Okay, it's really, really, really far away. Okay? So, but the galaxy is in the way of us seeing another galaxy behind it. So if we can't see the galaxy behind it, like how do we, you see that big circle around the outside? That is actually an image of the galaxy that's right behind the galaxy in the foreground. Okay? It's lensed. Now I'm going to show you exactly how this works, because it can be confusing unless somebody draws you a picture, which is why I have a whiteboard. Thank you, Zach, by the way, for bringing me a whiteboard. I really appreciate this. This makes everything better. Thank you, Zach. Okay, now let's say we have a galaxy here, okay? And then we have a galaxy here. And then we're here. You know, you are here. It's like a mall. All right, and then this is where the beer is. This is great, thank you. Now, okay, now light propagates in 360 degrees. Light propagates in every direction, right? If I go over here, I'm still seeing light from this, maybe from a different angle, but light is still reaching me from, say, this camera. Now this galaxy over here is not only sending light directly to us to see here, light is also going in every other direction. Okay? Now let's imagine that the light that's describing, you know, the light which carries the information of the atoms that it interacted with before. Let's say this light actually travels this way, and it would have never reached us. You wouldn't have seen it. Okay? I only see you people from my perspective, but if I was 8 feet to the left, I would see you from a totally different perspective. I would see different information coming at me. Different light would be reaching me. Okay? Now let's say that the light leaving this galaxy now interacts with this galaxy, which has a lot of dark matter, a lot of ordinary matter. This light will actually bend and then find us over here. Okay? So when we see pictures like this, that sphere that's around it, it's actually light that's produced in a cone, and then it actually is influenced by that gravity, and it comes back down. And because that path is diverted, it goes in a different direction. Go ahead.
So this is just like a telescope image? This is an untouched image?
Yeah, absolutely.
Just like photograph of the sky?
Yeah. Cool, huh? These are real photos. These are not like artist interpretations. These are real photos. The one on the left, that one's really, really, really far away. So, and they're kind of grainy because we're actually, if you look at the actual photo that was taken from the telescopes, these would be so, so tiny, but we zoomed in so that it's kind of pixelated because of that. Yeah, I believe actually on the right side, the two, no, it's a different photo. So there's another one where there's actually two galaxies on the inside of the lens, and they're actually the same galaxy. It's totally crazy, okay? But because of this, we can actually measure, because we can actually see the light. Believe it or not, people are smart enough to figure this out. But that ring on the outside, we can actually look at that light. Really smart people that went to school for this stuff, they can actually know the mass of the galaxy that's behind this galaxy in the foreground just by looking at the light and understanding exactly what's going on. And we can actually measure how much dark matter and how much matter is in the galaxy in the foreground. And this is another way we can measure dark matter. Yeah.
This might be like conceptually weird to ask, but like, is dark matter more or less dense than like normal matter? Because like it makes up the majority of the mass of the universe, and I know the majority of the universe is emptiness as far as we perceive it. And so that tells me that like even though it's the majority, but the vast majority of the universe is empty. So would dark matter have a very low density?
I don't know.
All right, fair enough.
There's your answer. But I can actually I can answer you. Okay. So the short answer is nobody knows, but everybody's thinking about that. Okay. Is dark matter something? Is it a particle? Okay. Is it a very okay? So do you want to get super nerdy with it? Is it a KeV particle? Is it a GeV particle? Like how much energy does this particle have? Has anybody ever seen this? I'm going to write one equation tonight. Has anybody seen that before?
No. Yes,
Yeah, the wrong
Hey,
case.
dude. You sold nuclear bombs to America, right?
Yeah, no, yeah, okay. So, energy and mass, what is this sign here? Equals. What does equals mean?
Assignment.
It's something is equivalent.
No, it's assignment.
Chat. We're making this easy for everybody. Okay. Yeah, we're gonna make this easy. Energy and mass are actually equivalent to each other. Okay, energy and mass are equivalent to each other. Now, when we describe the mass of something, okay, I'm going to give you an example here. Let's take I have my notes here. Let's say, okay, so let's say this is a down quark, which has a mass of approximately 4.8 mega electron volts divided by the speed of light squared. Okay, so a down quark is part of something that makes up a proton or a neutron. Okay, now when we say its mass, like how much does it weigh? We weigh it and we describe its weight by how much energy it has. Okay, because energy and mass are equivalent. Okay, so when we describe these things, so when I said, is dark matter like an MEV particle, is it a KeV particle, is it a GeV particle? So we have mega electron volts, we have giga electron volts, and this is E equals mc squared. What's the opposite of that? Divided by the speed of light squared. Okay, this is how we measure it. When we want to convert back and forth, we either multiply it by the speed of light or we divide it by the speed of light squared. So when we describe the mass of these particles, we're actually describing the amount of energy they have. Now, to answer your question, we don't know if it's in a energy level that's very, very small. Like there's one concept that it's neutrinos. Okay, neutrinos are very, very, very tiny. Okay, very, very low mass. How much is a neutrino? Electron neutrino mass. Okay, so an up quark, which is only one of three parts that make up a proton, is 4.8 mega electron volts. A electron neutrino is 2.2 electron volts. Very, very tiny compared to the mass of something that just makes up a proton. Okay, and a regular electron, 0.511. Okay, that's beside the point. So is it something very, very small, or is it something like in the, not mega, but let's say giga electron volts? Is it way more massive? Okay, like a top quark is 173.07 giga electron volts, which is about the mass of a gold atom. Like one quark, it can actually weigh as much as an entire atom of gold, which is what, it was in 93 or something like that. It's huge, it's massive, okay? So there could be a dark matter particle that's massive, that weighs like as much as a single gold atom. Who knows? Or it could be very, very small, you know, the size of like a neutrino. Or maybe there's a limit that's below the mass of the neutrino. That if there's a ton of them, you know, it could be that. Or maybe there's fewer of them and they're just more massive. There's another idea. Let's imagine that dark matter isn't dark matter at all. What if it's ordinary matter? What if this whole idea is wrong? What would it be? Some people say it could be black holes that we just couldn't see. Maybe it's clusters of brown dwarfs and white dwarfs, which is another model. I hope I don't lose you. I'm gonna shut up after this, I promise. But this is for the people that care a lot. So we had the WIMP model. We're gonna talk about what's the opposite of a WIMP? Macho. Nacho. Massive compact halo object. Massive compact halo object. That's what a macho is. Basically, it's black holes, it's white dwarfs, it's brown dwarfs. It's things that are so faint that we can't see them, but there's a lot of them, they clump together, and then just because we can't see them, but their mass is still there, we're gonna call that the dark matter. That's another model. It's probably wrong, so don't listen. But that is another model. And then I promised I wouldn't talk about this, but because I did end up talking about it for a long time. There's one more, which is... Does anybody know what that is? Zach.
It says bond.
What does it stand for?
Massive orthogonal normal distribution.
Close. Not really. It stands for modified Newtonian dynamics. And I'm losing everybody, so this is fine. But for the nerds, modified Newtonian dynamics means that the entire theory of gravity is wrong altogether. Yeah. Yeah, totally. There are people working on this that, you know, and there are...
Hey, but you know, they threw out the whatever his name is for your son.
Sure. Yeah, totally. Sure. You know, who knows? The answer, I mean, the whole point of this is it's super cool. Like most of the universe, we don't even know what it is. But that's like a call to action. Like that's why we should be excited we have something to learn. Okay? I did my best to try to explain to you how it works. How do we know it's there? How do we prove that it's there? I mean, even if we find out that dark matter isn't what we think it is, or maybe we're measuring it all wrong, like this is us throwing our hands up and saying we don't know everything. That's like the best thing about this entire exercise. Is I can give an entire talk, and basically the premise of the entire thing is I have no clue. You know, I kind of have an idea of what it's doing, but we have no clue. And there's really smart people working on this. It's super awesome. And I mean, and it makes up everything. I mean, we make up such a small thing. We think we're so important, we're so special. And we kind of are because we're rare. You know, we're super rare. The majority of the universe is this big, homogeneous force that's pushing the universe apart, and then there's all this dark matter that has all this responsibility, but we're like made up of this really, really exotic stuff called baryonic matter, like atoms. We're made of something super exotic, we're super special, and we should celebrate that. That's super awesome, but also know where we came from. You know, we owe the existence, the way we know it, to the existence of dark matter, whatever it ends up being. That's super awesome. And that's all I'm going to say about it tonight. These always go longer than I anticipated, and all right. Okay. Thank you guys. There's. You have one more question? You have a whiteboard question? Go ahead.
So you said massive light.
Yeah.
How do we not see it? Well, for massive light is zero. How do we calculate how solar?
single photon carries a very specific energy.
I'm wondering how it came if it doesn't have because this is saying that mass is or so I don't like that, Billy.
Yeah, so I'll tell you what, a big secret. I don't have these ideas because I have the same idea. I personally have this idea that mass and